Two teams of scientists set out to measure the exact same thing: how fast the entire universe is growing, using two of the most precise methods humanity has ever built. They should have gotten the same answer. They did not. And the gap between their numbers has become so stubborn and so impossible to explain away that it may mean our entire picture of the universe is quietly, fundamentally broken. Here are the two numbers because they're the whole story. One team says the universe expands at about 67. The other says about 73. That's it. That's the crisis keeping cosmologists up at night. It sounds like a rounding error you'd shrug off. But stick around, because the reason those two tiny numbers refuse to agree might be the crack through which the next revolution in physics comes pouring out. This isn't two groups being sloppy. Both answers are among the most carefully measured quantities in all of science. And that's exactly what makes it terrifying. Let's start with the thing everyone gets wrong about the expanding universe. The universe expanding does not mean galaxies are flying outward through space, like debris from an explosion. It means space itself is stretching everywhere all at once. Imagine dots drawn on a balloon. As you inflate it, every dot moves away from every other dot, not because the dots are traveling, but because the rubber between them is growing. You're a dot. Every galaxy is a dot, and the whole balloon is swelling. So here's your first mind-bender. There is no center of the expansion. From every galaxy in the universe, it looks like everything else is running away from you. You're not special. You're just standing on your own dot, watching the rubber stretch. Now, who figured this out? You probably learned one name in school: Edwin Hubble. But the story is a little more crowded and a little more unfair. In 1912, an astronomer named Vesto Slipher noticed that light from distant galaxies was stretched toward the red end of the spectrum, a clue that they were rushing away. Then in 1927, 2 full years before Hubble, a Belgian priest and physicist named Georges Lemaître worked out that the universe was expanding and even estimated the rate. He published it. Almost nobody read it, partly because it was in a small French journal. Then in 1929, Edwin Hubble, with a giant telescope and a knack for publicity, laid out the evidence so clearly that the world finally listened. For decades, the expansion rate was called the Hubble constant. Only recently did astronomers officially add Lemaître's name back on. History remembers the loudest voice. It doesn't always remember the first. Would you have believed a quiet priest over a famous astronomer? Whatever you call it, this number, the expansion rate, is one of the single most important numbers in all of science. Nail it down, and you can calculate how old the universe is, how big it is, and how it's going to end. Get it wrong, and every one of those answers shifts. So you'd think, a century after Hubble, we'd have it pinned to the decimal. We don't. And to see why, you need to see the two completely different ways we measure it, because both are gorgeous and they're at war. Method 1 is called the cosmic distance ladder, and it's exactly as clever as it sounds. You can't just stretch a tape measure to a galaxy, so astronomers build a ladder of steps, each one calibrating the next. The first rung rests on the work of a woman who should be far more famous than she is, Henrietta Swan Leavitt. In the early 1900s, working at Harvard for a fraction of a male astronomer's pay, Leavitt studied a special kind of star called a cepheid. These stars pulse, brightening and dimming on a regular beat, and Leavitt discovered something magical. The slower a cepheid pulses, the brighter it truly is. That means if you time its blinking, you know its real brightness, and if you know how bright it really is and how dim it looked from here, you can calculate exactly how far away it is. She turned a blinking star into a cosmic tape measure. Nearly every measurement of the distant universe still stands on her shoulders. From there you climb. Cepheids get you to nearby galaxies. In those galaxies you find exploding stars, type I supernovae, which all detonate with almost the same brightness. So they work as mile markers you can see from staggeringly far away. Step by step, rung by rung, you measure your way out into the deep universe. Watch how fast those galaxies are receding and calculate the expansion rate. The team that does this most precisely is led by an astrophysicist named Adam Rees, who already has a Nobel Prize for co-discovering that the expansion is speeding up. His project, called SH0ES, has spent years refining every rung of that ladder. And their answer? The universe is expanding at about 73. That's method 1. Feel free to trust it. It's built on a century of careful work. Now let me show you method 2, which is just as careful and which flatly disagrees. Method 2 doesn't climb a ladder at all. Instead, it reads the universe's baby photo. About 380,000 years after the Big Bang, the cosmos cooled just enough for the first light to travel freely, and that ancient light is still arriving today, stretched into a faint glow of microwaves coming from every direction in the sky. It's called the cosmic microwave background, and it is the oldest thing you can ever see, a snapshot of the infant universe. A space telescope called Planck mapped that glow with breathtaking precision, capturing tiny ripples in it that encode the exact ingredients of the early universe. How much matter, how much dark matter, how much energy. And here's the clever part. If you know precisely what the universe was made of back then, you can take our best physical model of the cosmos and run it forward like winding a clock to predict how fast the universe should be expanding today. You never measure a single nearby galaxy. You calculate the answer from the beginning of time, and that answer comes out to about 67. So look at what we have. Read the universe's baby photo and wind it forward, 67. Climb the ladder of stars and measure the real thing today, 73. Two numbers, same universe, and they will not shake hands. Now, for a long time, this was fine. Both methods had big enough error bars, enough fuzziness, that the two numbers overlapped, and everyone assumed they'd eventually meet in the middle. Here is the part that turned a curiosity into a crisis. As both methods got better, the fuzziness shrank, and the numbers didn't move toward each other. They dug in. The distance ladder kept landing near 73. The baby photo kept landing near 67. The gap didn't close. It sharpened. Scientists measure this kind of disagreement in units called sigma, and there's a famous threshold, 5 sigma, the gold standard, meaning the odds of it being a random fluke are about 1 in 3.5 million. The Hubble tension has crossed 5 sigma. In the language of physics, that means this is not an accident. This is real. Something is genuinely wrong. Doesn't that give you a little chill? Two of our best rulers, measuring the same room, and one insists it's bigger than the other. So who's the culprit? For years, the obvious suspect was the latter. It has a lot of rungs, and every rung is a chance to make a subtle error. Maybe the cepheids were being measured wrong, maybe dust or crowded star fields were throwing off the brightness. It was a reasonable accusation. So Adam Rees turned the most powerful telescope ever built, the James Webb Space Telescope, onto those exact cepheids to check them with fresh, sharper eyes. If the latter had a hidden flaw, Webb should have exposed it. Instead, in results over the last couple of years, Webb largely confirmed the measurements. The latter held. The 73 didn't budge. The obvious escape hatch slammed shut. But science is never that tidy, and there's a genuine plot twist. Another brilliant astronomer, Wendy Freedman, has spent her career on this exact problem, and she uses a different rung for her ladder. Not cepheids, but a method based on the brightest red giant stars, which sidesteps some of the messiness. And her results have tended to land lower, closer to the middle, sometimes flirting with the CMB's 67. So now there's a real, ongoing scientific fight happening in journals and conference halls right now. Today, over whose ruler to trust. This is not settled, and that uncertainty is exactly what makes it one of the most exciting problems in physics. Because if the measurements are both basically right, and that is looking more and more likely, then the problem isn't the rulers. The problem is the map. And that is the possibility that makes cosmologists both terrified and thrilled. Remember, the 67 isn't really a measurement of today's universe. It's a prediction. It's what you get when you take the baby photo and run our standard model of the cosmos forward. So if the true expansion today really is 73, it might mean that our standard model, the one that has passed nearly every other test we've thrown at it, is missing an ingredient. Something happened between the baby photo and now that our equations don't account for. Something we have never seen. And people have ideas, each one wilder than the last. One leading proposal is called early dark energy. The idea that in the first fraction of a second, the universe was briefly filled with an extra push of mysterious energy that flared up and vanished, subtly resetting the expansion. Others suggest that dark energy, The force accelerating the universe isn't constant at all, but changes over time. Others point fingers at exotic, undiscovered particles or whisper the boldest idea of all, that gravity itself might behave differently on the largest scales than Einstein taught us. Every one of these would be a genuine rewrite of the physics textbook. Any one of them, if confirmed, would be the discovery of the century. And this is why working scientists don't see the Hubble tension as an embarrassment. They see it as a doorway. Look at history. The last time our best theories gave two stubbornly different answers to a simple question, it wasn't a mistake to sweep away. It was the loose thread that unraveled everything and rebuilt it better. A tiny wobble in the orbit of Mercury helped hand us Einstein's relativity. A strange glitch in how hot objects glow cracked opened the entire quantum world. The universe tends to hide its biggest secrets inside the small numbers that refuse to line up. And here we are again, staring at a 6-point gap between 67 and 73, and it may be pointing straight at the next Einstein. And before we zoom back out, here's a consequence that makes this whole abstract argument suddenly feel personal. That expansion number is tied directly to the age of the universe. A universe that expands faster reaches its current size sooner, which means it's younger. So when these two camps fight over 67 versus 73, they are, without ever saying it out loud, arguing over how many birthdays the universe has had. The baby photo number gives the familiar age you've heard your whole life, about 13.8 billion years. Push the rate up towards 73, and the cosmos gets noticeably younger, potentially by 1 billion years or more. Sit with that for a second. We have telescopes that can photograph galaxies from the dawn of time. We can capture the literal afterglow of the Big Bang. And we still cannot agree to within 1 billion years on how long everything has existed. Nobody actually knows how many candles belong on the universe's birthday cake. And if the phrase dark energy is ringing a bell, good, because this is where that mystery thickens. Dark energy is the strange pressure pushing the universe apart faster and faster, and it makes up most of everything. If the fix to this whole crisis turns out to be that dark energy behaved differently in the past, then the Hubble tension isn't just a disagreement about a number. It's the universe hinting that the biggest, most dominant force in all of reality is stranger than we ever wrote down. The little 67 versus 73 argument could be the loose thread hanging off the largest thing in existence. So let's bring it home to you, standing on your one little dot. The expansion rate isn't an abstract number on a chalkboard. It sets the age of a universe you were born into. It sets the size of everything that exists. And it decides how your universe ends, whether it drifts apart gently forever or something stranger. The unsettling, wonderful truth is this. We are living inside a cosmos whose most basic property, how fast it is growing, right under our feet, we cannot yet agree on. The two best answers humanity has differ, and both are correct, and that should be impossible. So the next time someone tells you science has it all figured out, you can smile and tell them about the number, about how we built two magnificent machines of thought, one that reads the first light of creation and one that climbs a ladder of blinking stars, pointed them at the same simple question, and got two answers that both refuse to be wrong. One of them is hiding something new about reality. We just don't know which one yet. So what do you think is broken, our rulers or our understanding of everything? Because somewhere in that stubborn little gap between 67 and 73, the universe is trying to tell us something. And the moment we finally listen, the story of your entire cosmos is going to change.